It's Wednesday, November the 20th, and this is Babbage, a weekly conversation about science and technology. I'm Jan Piotrowski, the online science and technology editor.
And I'm Tim Cross, the science correspondent.
This week we'll be talking about acidifying oceans, Boeing's new foldable airliner, and making batteries using viruses. Tim, one of the less talked about consequences of greenhouse gas emissions into the atmosphere is how they lead to the acidification of oceans, and two new reports have come out describing the process and the consequences.
That's right. So a lot of the discussion on climate change talks about global warming, because greenhouse gases, the clue's in the name, they tend to make the planet hotter. But carbon dioxide, which is the sort of chief man-made greenhouse gas, has other effects as well. One of them, this stuff goes into the atmosphere. A lot of it then over time ends up being absorbed by the oceans. When it gets absorbed by the oceans, it forms something called carbonic acid, which is a weak acid, and that changes the natural pH of the water. And people have been worrying about what this might mean. It's flown a bit under the radar compared to the talk of higher temperatures, but it's potentially sort of pretty significant. So, yeah, there are these two new reports out. One looks at the science, one looks at the likely economic impact of it, and sort of rather infuriatingly, but familiar to anyone who follows climate science, they come to the conclusion that on the one hand, on the other hand, and it's kind of hard to know.
So what would be the consequences of oceans becoming more acidic?
The main consequence is going to be on the animals that live in them, and the exact effects depend on what kind of animal you are. So if you're something that uses the minerals dissolved in seawater to build a hard shell, then the more acidic the ocean is, the harder work that is, and for some sort of species it might become impossible. It's already impossible in some parts of the ocean. In cooler waters it's more difficult. The sort of band in which these species can't exist will probably sort of move towards the equator over time. I mean, we should say this isn't theoretical. We can see this stuff happening already. You can measure the pH of seawater, and it's already changed sort of quite considerably, even since the 1980s when people started taking reliable measurements. But it might not all be bad news, because the other effect is you have more carbon dioxide in the water. If you're a photosynthetic organism, then that's good news, because for you carbon dioxide is food. It's you need it for your metabolism, and these photosynthetic organisms are the base of the entire oceanic food chain. So if their productivity goes up, there's more of them around. They'll support bigger populations of predators. In some parts of the ocean it might actually be a net sort of gain for biological production. We know that these things will happen, both of these things will happen. What's a bit less clear is whether the extent to which they'll balance out, whether one will dominate, and what the net effect will be.
So we can expect more big fleshy fish, but fewer crustaceans, though they might be easier to peel.
Yeah, and I understand that Boeing, the big American aircraft maker, are designing a new plane, and this time it's out with the fancy carbon composites and all-electric planes and batteries that catch fire, but in with foldable wings.
That's right. Boeing announced that it will be making its 777X airliner, which it hopes to bring to customers in about 2020, if all goes well. Indeed, it's ditching the technology that caused it so much trouble with the 787, which is its previous big bet in passenger airliners, and which, as you mentioned, has had a few glitches along the way. It first of all was delayed because of the new production chain that Boeing implemented by outsourcing a lot of the development work to subcontractors. So it will be bringing a lot of it back in, and second of all, it will actually revert to an old airplane, an aluminium fuselage, which it has used for decades on its 777 aircraft.
So it's back to the 1980s for the fuselage, but the foldable wings are new. What's the idea behind those?
So a longer wingspan means that a plane can be more fuel efficient, and fuel efficiency is the thing that airlines, which are the primary customers of these craft, are very concerned about these days with high fuel costs. So a rule of thumb says that a 1% cut or 1% increase in fuel efficiency means $1 million saved over the lifetime of a plane for an airline, which is not insignificant, especially if you have a large fleet. So with the longer wingspan, the Boeing should be about 12% more fuel efficient than its competitors from Airbus, which is the European rival to Boeing.
So those are the benefits of a longer wingspan, but why the need to fold the ends?
Well, the basic reason is that anything with a wingspan larger than about 65 meters will not fit in the airport gates in most of the airports around the world. Now, that's one of the major limiting factors in airline development these days. It's not that technology couldn't be used to create very fancy whizzy aircraft. It's that these fancy whizzy aircraft need to fit into the existing infrastructure. So the reality on the ground is what limits aircraft development in many ways. And with these foldable wings, which fold at 3 meters on each side, the wingspan will total about 71 meters. And therefore, with the wings folded up, will be just about 65, making it fit into those standard gates. Boeing has managed to circumvent this problem at the same time as introducing fuel efficiency savings into the new model. Tim, materials scientists have been looking for whizzy new materials with which to make more efficient batteries. But now they're looking to biology.
That's right. So there's this team at the Massachusetts Institute of Technology, and they're working on something called a lithium-air battery. Now, the problem with batteries is that they're very convenient and they power, smartphones, and they're even starting to power cars, all kinds of things. But their energy density isn't very good. In other words, if you take a kilogram of batteries and compare it to a kilogram of, say, petrol, you get a lot more energy out of the petrol than you do from the batteries. One way to hopefully improve the performance of the batteries is to make the materials more sort of technologically advanced, snazzier. And this team have come up with quite a sort of novel way of doing it. So batteries convert, they use chemical reactions to generate electricity. And one area of investigation is in the sites in the battery in which those chemical reactions take place. So if you can increase the amount of surface area that you've got for the reactants to mix together, then you generate more juice for a given weight of battery. And this is nanotechnology, it's nanoengineering. Of course, nature's been doing nanoengineering for billions of years. Cells and microorganisms are sort of little nanoscale workers that move things around, stitch them together and make all kinds of interesting materials. So this team, led by somebody called Angela Belcher, decided that they wanted to use viruses to build their batteries.
So how can you use a virus to build a battery?
So we should say these aren't viruses that infect people. These are things called bacteriophages, which are viruses that infect bacteria. And really a virus, it's just a sort of small nanomachine that transports DNA around and injects its own DNA into places where, it sort of shouldn't be. It hijacks cells to manufacture more copies of itself. What the researchers did was they genetically engineered their viruses, changed their behavior so that they would latch onto molecules of manganese held in a solution of water. Then these manganese-coated viruses would then be used to build tiny nanoscale wires that form the cathode of the battery. The traditional way of making these nanowires gives you very smooth wires. It turns out that using the viruses makes them rough and spiky, and that means they have a higher surface area, so you can get more reactants onto a given wire and get more current out of it.
So this is a lab experiment, but is it possible to scale this up to make it into an industrial production process?
It isn't clear. They did some work in 2009 which looked promising. When that was scaled up to industrial production, they eventually fell back on sort of traditional, big industry methods, and the sort of natural production methods were only a sort of an inspiration. On the other hand, there are some advantages to this. So building batteries traditionally requires big factories, lots of nasty chemicals, high temperatures, and all the sort of paraphernalia of industrial production. This stuff works at in a lab, in a room at room temperature, in a vial of water with some materials in it. So it's much, much easier to do. So it may scale up, but what the researchers say is, even if we end up producing these wires with some other industrial process, it was the sort of nature's ability to put these things together that inspired them to create them.
Thanks, Tim. That's all for this week. If you have any comments or feedback, please visit our Babbage blog at economist.com/blogs/Babbage. In London, this is The Economist.